Yeah, hi everyone. We are the Sparty Design Group, and we are sponsored by the Student Alumni Foundation. I'm Matham Al-Eid.
I'm Brian Rockwell.
I'm Ashley Glizicki.
Diana Tone.
My name's Nima Stewart.
Ahmed Zahid.
All right, say your names again when you come up to present.
Yeah.
Please, just so I can keep a record.
Okay, so I'm Matham. The goal of our project is to design a cooling system for the Spartan mascot. And currently there is no cooling system inside or outside the Spartan mascot. And during the summer months, the temperature are very high. So let's say for a basketball game, the temperature can range from 30 to 40 Fahrenheit degrees, 15 to 20 degrees in Celsius above the ambient temperature. And we observe a temperature as high as 98 Fahrenheit degrees, 37 degrees in Celsius, which is, this temperature is very close to the body temperature, indicating that very little cooling is taking place. So we observed a number of parameters for our design, and we came up with 9 parameters. The first one is safety. Safety is the most important part for any design or project. In our case, we want to make sure that the person who's gonna wear the mascot, the costume, be safe all the time. The second thing is cooling performance. Since the main goal of our project is to cool Sparty down, so we need to maintain a specific range of temperature inside the costume. And the third one is mobility. Sparty is forbidden from talking to anyone, so his body motions are the only way to communicate with people. So we're gonna do our best to keep them as they are. And the fourth one is duration. The current time that Sparty can be in action is an hour, 1 hour at best, and this is limited by safety concerns related to the dehydration and the overheating. The fifth one, the durability. The device should be durable to allow multiple uses and minimize the upkeep costs. The sixth one is the noise. We want the device to be quiet, no noise. The Sparty need to get instructions from his teams, so noise is not good choice. And the seven parameter is weight. We need the device to be lightweight as possible, no more than 15 pounds for the device. The eighth parameter is the cost. We're gonna do our best to minimize the cost, to not go over the budget limit. And believe it or not, the Spartan mascot is washable, so we need to keep it like it is and to make it washable as possible.
So I'm Ashley again. So we came up with 5 different design ideas to be able to try and figure out which one is the best. The first one we came up with is a Peltier junction. A Peltier junction ends up, when you connect it to a battery, it'll create one side that is hot and one side that is cold. By utilizing the cold side, we can then possibly effectively cool down Sparty by using multiple of them strategically placed around the suit. Our second option that we came up with was a phase change material. A phase change material, simply stated, is like an ice cube. It melts when it becomes above the freezing temperature. There are multiple different systems that are out there currently, and they range in the sizes and their temperatures that they cool at. Some of them are at 50, 55 degrees Fahrenheit, some of them are around 80 degrees Fahrenheit. So that way then when Sparty's in the costume, it only starts melting when it gets really warm in there. There are currently quite a few research studies out there for firefighters and military, since firefighters have to go into a blazing hot house that's on fire, and also military since they're wearing all that heavy equipment. So we currently have some samples right now that we are looking at, so we can pass them around so you can see kind of more exactly what a phase change material is and some of the different types. Then we also found out from other research that there are water suits out there. However, that requires Sparty to be carrying around water with him that isn't really doing anything unless he's hooked up to a battery and a pump. Since that makes a lot of noise and it wouldn't really be feasible to carry around that much of equipment, we were thinking about high pressure air tanks, where then we would have tubing attached to like a vest or a shirt that Sparty is wearing, and then he can come up and get blasted with air during intermittent times. Or else with an internal tank that then we were to embed right into his arms or somewhere. So that way then there could be a control system, so that way then there's a switch that either the escort or just pressing a button could end up turning on. And so that's another idea. And this is a picture of a cooling shirt, and they just sewed those tubes on there. So it is possible to be able to have tubes that you sew into a shirt, possibly do something. And then our fifth design idea was combining the external high pressure air tank by having the tube sewn into a vest that has phase change material in it. So that way then Sparty can have phase change materials cooling him down constantly, and then he can get blasted with air when he needs more of a cool down.
I'm Diana Tone, and for our 5 design ideas, we evaluated the pros and cons of each. The first one is the Peltier junction, and with the Peltier junction, it enables us to have a control system to maintain the temperature within the suit. However, the disadvantage to that is that it does have a hot side, and the hot side can reach really high temperatures, which requires us to have additional equipment, such as a heat sink in order to help with the cooling performance. Our second design idea was the phase change material, and with phase change material, it will be fitted into a vest and have phase change packs that can be fitted in the vest so that the weight and the material can be distributed to the areas that we want it to. And depending on the type of phase change material we use, we can set the temperature of the phase change. The disadvantages to the system is that phase change materials are difficult to manufacture, and it does have a limited heat capacity, so it'll get warmer as time goes on. We had the design idea of a high pressure air system. We had the external and the internal one. They both have the same idea behind them, that we can cool via convection as well as evaporating some of the sweat to give some relief to the user. With the external system, it's a quick hookup to an external air tank, so it can offer quick relief. However, the disadvantage to that is that it is a quick relief and that it doesn't offer continuous cooling. So, and there's also noise associated with it. With the difference with the internal system is that the air tank would be embedded in the suit, so that it can cool the user continuously. However, since the air tank is embedded in the suit, that limits the capacity and the size of the air tank. And for our last design idea, it combines the external high pressure air as well as the phase change material vest. So that kind of combines the qualities of each. And again, it can provide continuous cooling because of the phase change material, as well as give quick relief and evaporate some of the sweat by utilizing the high pressure air. And again, the disadvantages to that is the noise from the high pressure air system, as well as because we're combining two design ideas, we have to pay more attention to if we can fit everything in the suit.
And again, I'm Ashley. And we took our original design criteria that we had stated, that Mason had stated earlier, and we really rated them amongst each other. So a score of 2 means that it's a lot worse than a score of 5 for this one. And then we used our weight to create a weighting score, and then we were able to figure out that the two top ideas were the phase change vest and the combined phase change and high pressure air. And this allowed us to throw out some of our lower design ideas, which would be the Peltier junction and the internal high pressure air tank.
Okay. So once we had selected the designs that we thought were the most promising, we started doing some modeling to get some real numbers that we could, oh, I'm sorry, I'm Brian Rockwell. So we could get some numbers to predict the actual performance of these systems. So we started by looking at models of heat generation in the human body. And the first model we used was a published model that looks at weight, height, and age, as well as the level of activity. With this model, we predicted 329 watts of heat generation in Sparty when he's at a game day or walking in a parade. And then the second method we use looks at metabolic equivalent and presents the metabolic rate as just a function of weight and the activity level. And based on this one, we predicted 325 watts. We were really happy that with two different models, we got very close results, so we feel that this is fairly accurate. So we looked at it as our natural mode of heat loss, respiration, because even though Sparty is quite insulated, he's still breathing in and out. And you actually lose a lot of heat just through your breathing. And there's two effects there. One is that you breathe in relatively cold air, you know, the body heats it up, so you're losing heat, breathing out relatively hot air. And secondly, you're breathing in relatively dry air, and it's evaporating water in your lungs, just the same way that sweat evaporates off your skin and cools you. So our predicted cooling from evaporation is 55 watts, which means that our net heat generation, net heat addition from the human body into the suit is 274 watts. So this is what we're trying to get rid of. So the first model we did was for the high pressure air system. And like we mentioned with respiration, there's two cooling mechanisms, the convection and the evaporation of sweat. And both of these are a function of air velocity through the suit. And we found that depending on the velocity, the cooling due to evaporation is 1.5 to 2 times that of convection. So, you know, evaporating the sweat off your body is a lot more effective than just having air coming across a dry surface. And we found that at a flow rate of 5 meters per second, we got 980 watts of cooling. And if we can safely and comfortably double that speed to 10 meters per second, we get 1,560 watts of cooling. So we found that with these systems, we're able to get a lot of cooling very quickly. So we think that this is going to be an effective system. And then the next system we looked at was our phase change material. And we found that most of the phase change materials, like what's being passed around, have heat diffusions around 200 kilojoules per kilogram. And we're thinking that we can, you know, comfortably distribute about 2 kilograms of this material within the suit, which gives us 400 kilojoules of energy that we can remove. So going back to the 274 watts of net heat addition into the suit, that means for 24 minutes we can absorb all the heat that the human body is generating. And we're not expecting that we're going to have 100% efficiency, that we can actually capture 100% of the heat that's generated. So we're expecting that this system will be effective for much longer than, perhaps double that amount of time, and provide substantial cooling relief over an extended period of time.